This is the first of 3 videos that will discuss elements in general. Not every single element of the periodic table, but the ones that really are sort of getting a lot of attention for applications and fabrication of either smart materials, plastics, agricultural compounds, medicines. So we're going to look at those elements that are really significant in synthesis or in high demand, and we're going to divide them into kind of 3 groups. We're going to look at, first of all, the kind of the S block. If we were to kind of just visualize the periodic table, you kind of have really 3 parts. The main part of the periodic table, you have the S block, the D block, and maybe you remember this would be called the P block. So it really has to do with those orbitals that we now know from quantum mechanics are present around the nucleus for the electrons to sort of sit in. And the S was more spherical, dumbbell, and D you get a wide variety, like clover leaves. You get 5 different D orbitals, and that's why we have so many boxes here. It's because 5 times 2, because you can have 2 electrons in each orbital. If you have 5 orbitals, 2 electrons that can go in each, you can have 10 sort of different types of occupations of the D level. So there's also, we are going to get into a little bit of the lanthanides and actinides, and just remember these are kind of the rare earth. The first, I guess, series is the lanthanides. Those are also called rare earth elements. The reason we'll see is because they're kind of hard to find. As you go farther down in the periodic table, it is typically harder to find those elements because they're just larger. It took more to make them in those explosions of stars and such. So just remember, we're going to sort of divide it into then the S block. We're going to look at then the D block. We're going to take a break from looking at the what's called main group elements. The S and the P are the main, or they're called the representative elements. We're going to sort of put in the middle before we go on to the non-metals over in the P block. We're going to talk a lot about transition metals. There's a lot going on in terms of chemistry in this area. As we get to the next slide, we're going to try to look at the size of not just the atom, but when it's charged. The natural form, solid, liquid, or gas, what does it typically come in as a element? And then the abundance, how much of it do we have for use in making things? So looking at our periodic table, this is not a Van Gogh drawing. This is given to us this way to kind of show that the area of the box for oxygen here is proportional to the amount of it available in the world on Earth. So we can look at the periodic table in a different way, and we can say, hey, in general, as you go down your groups, this would be the this would be alkaline earth metals. We have the start of our D block, but then inside of that, remember the F block, those lanthanides really are up in there, but the periodic table will be too long, so we sort of tend to put them underneath the periodic table. They're represented, and there's not a lot of these these lanthanides relative to, let's say, our hydrogen, carbon, nitrogen, oxygen, fluorine. So in general, just realize that the trend is you have less of this stuff at the bottom of the periodic table than you do at the top. That's in general. Now, taking one column here, it is interesting to note that we have a lot of hydrogen, and universally, or in the universe, you have quite a bit of hydrogen. We have that as our smallest element, and that's what, like for the sun, it's hydrogen and helium. So talking about the universe, it might be different here, but we're talking about the world with Earth and rock. We tend to have more of these represented down in the bottom parts of the periodic table. But notice this, the lithium's not as prevalent as sodium. That's interesting, but it's just a kind of anomaly, but as the trend continues, we do get smaller and smaller. Now, it is unfortunate that we don't have as much lithium as sodium or more, because you notice this little cell phone symbol. This chart has overlaid on top of how much is present in the world, kind of what is used for cell phone technology. And I love this because, boy, the fabrication of a cell phone, which I'm actually shooting this video with, the representation of the elements in cell phone design is prevalent. You don't just have 20 or 40. I have over 60 different elements from different parts of the periodic table that go into making your cell phone or smartphone or probably your laptop, your iPad, some of the same touch screen technology. These rare earth elements way down here at the bottom of the periodic table, like europium, erdium, they are important not just for colors of your cell phone and your displays, but also for the ability to have a touch screen. But if you get over here to, I guess, gallium and arsenic, tin, indium, antimony, some of these can be important for the microphone technology, or sorry, for the speaker technology, vibration technology. Of course, silicon is going to be for the chip. Carbon is going to be for the graphene that's in your battery. So there's just a wonderful display of how elements from all over the periodic table can be brought together to make some really cool things that we have in our world. And you say, well, it's not that big of a deal. Did you know like 54%, they say right now, it's probably climbing, of the population on not just the United States, but Earth, 54% of the folks have a smartphone. That's just phenomenal to kind of compare that to 30 years ago, just having something that was common amongst everybody. That's not likely, but now this is our connection, is a smartphone, a smart device. And within those devices, we have quite a bit of different elements. So just to kind of put three categories together for where all those 60 elements can be put into the design of the cell phone, you kind of typically have the screen, which is silicon, aluminum, oxides of those two metals, and maybe some potassium, they say, to give it more strength. I don't know the chemistry of that, but it's probably some very in-depth, cool chemistry that helps your screen become stronger and maybe resistant to scratching and cracking. But then there's also, within the battery, you have to have kind of the transfer of an ion, and the one they've picked is lithium because it has such a high charge capacity, or has a very high potential, cell potential. When you go from lithium plus to just lithium and you add that electron, there's a lot of energy in that transformation. So they've picked on lithium cation as our ion that transfers back and forth between a cathode and an anode. And in the anode, they've used carbon in a graphene form. In the cathode, they use cobalt oxides. Aluminum maybe for just the casing of the battery, and lithium is that charge that goes back and forth to give us our life in the battery, the function that supports. It's supported by lithium's mobility. We also have the chip technology, the motherboard, you might say, the soldering, the copper wiring, the transistors, the capacitors, the dopants that go into silica. There's quite a few. Not just you still have this here is our rare earth metals, these ones in kind of a off purple. The yellow here is, I think, our transition metals. Oxygen, of course, is our non-metals. We have some of your arsenic and antimony would be in your metal, the semiconductors. So silicon, would also be in that sort of semiconductor area. So there's just a lot of different elements represented in the cell phone. All right. All right, I want to talk about size of the atom and also size of the ion. So they're kind of different, of course. If you take this lighter blue, that's going to be the size of the atom for lithium, but there's a big difference you can see. As you take one electron away, it becomes very, very small. This sort of inside gray. I'll just darken it up a little bit. That would be representing the size of the lithium ion. It's interesting to notice it's very, very similar to the size of the magnesium 2+. So it turns out that these two, magnesium 2+ and lithium, can often be used in some of the same sort of chemistry. And I'm going to just give you one of them. So these metals, we'll just say M, can be bonded to organic groups, and R would be something like a methyl group. So we can have a metal like lithium actually make not just a completely ionic, but somewhat covalent bond, because it has such a high charge density. It can have a pretty strong interaction with this methyl group, CH3, and that's very rare. Please understand, most metals don't bond to carbons directly. They'll bond to them in terms of like a carbonate. I may put it down here, you might see a carbonate we have something like this, and that binds to calcium 2+. But we have here now, it's the oxygen carrying the negative charge. In these cases, it's the R group that almost has, I'm going to say a full negative charge, but it almost has, it has a very, very strong delta negative charge, maybe 80% of what a full negative charge would be, we have on this R group. It is a significant, I guess, fact that bonding lithium or magnesium to an R group gives us something like what we have here, a negative on an oxygen, we get almost a full negative on a carbon. That opens up the door for a lot of chemistry in the organic world. A couple other things I just want to say about the size. Notice some trends here that as you go down, in general the size of the ion or atom goes up. As we go across, they tend to go down. It's not as I guess, pronounced in the D block. They tend to not change too much as you go from left to right in size. It does somewhat go down, but not as much. But you can see a very extreme drop here in your P block. So there's a little bit of a difference. The D block then gives you a little more flexibility on which metals you might use, because size does matter. If you have a larger surface for the ligands, we're going to learn later on, can bind around a metal. So just kind of think of ligands as just organic groups that can have a binding site. Let's say this is our metal. So size does matter. Charge matters because it'll affect how strong this bond will be between something organic as a ligand that's bonded to that metal surface. We'll learn more about the terms ligands in the next video. Oh, and one last thing, please, in the PDFs that you have available to you, make sure you check out these links for each of these types of metals. And most of these, I need to say, are metals. Lithium was the lightest of all the metals. We have, though, if you look at your halogens, F2 is a gas, Cl2 is a gas, but bromine starts to be a liquid, and iodine can be a solid. So you have phase changes, kind of go from gas to liquids to solids for your halogens. Your nonmetals are less dense than the metals, and of the metals, which are, again, more dense and heavy, lithium's the lightest. So remember those facts and those things you can also learn as you open up these links under alkaline, transition metals, metalloids, which are kind of like metals but not completely. Then also open up this one on halogens and how they're used. Halogens are represented often as X. In bonding with organic groups, a lot of those types of compounds are used in organic chemistry. Okay, I'm going to stop with the next slide here because it's involving our alkali metals and alkaline. Let me get an alkaline. We're going to talk about alkali metals first and then come to alkaline. All right. So looking at alkali metals, lithium and sodium, they're not like hydrogen. Remember that hydrogen is a gas. It's in the form H2. These are metals. You have lithium solid and Na solid. So they're very different. They're sometimes confused as being similar because hydrogen is in the same column as lithium and sodium, but this is a non-metal. These are metals. A couple things just to kind of point out is when we look at production of each of these three, the first one is very, very different. We typically, you can use hydrolysis, you can take water and split it and make hydrogen gas and oxygen gas, but one of the main ways we make hydrogen is kind of have a low oxygen environment. We heat up methane in the presence of water, and from that we get sort of a change from the hydrogen bonded to carbon and having an oxygen take its place. Basically that's what's going on. All the H's are coming off from the carbon. We're making carbon monoxide and 3 hydrogen gas molecules. Now just looking at this from what you learned about entropy, which side would be favored? The side that has 1 methane and 1 water molecule, and these are going to be in gas form, steam with the gas methane, to 1 CO molecule and 3 hydrogens. I hope you're saying this side would be favored entropically. You get 4 out of 2 on this side. But it turns out, even though that's true, it's not a enthalpically favored reaction. So our kind of from Gibbs equation, we need to remember that to drive this reaction, we're going to have to take the T and make that very high so that we can dominate the reaction with the delta S, so we can get a lot of this product. Because the enthalpy of this reaction, the delta H, is actually going to be positive. There's one thing that kind of tips you off about that, is because this water, if you ever form water, it's typically very favored. Water is a very good product to make if you want to drive the reaction towards that side. You have water on that side. But we're driving away from water. So it's kind of typically, not always, is going to be then enthalpically not favored to go away from water and to go to something else. It's very, very polar. There's some things that go into why this is enthalpically often favored. But in general, we can drive this reaction by increasing the temperature. We can make a lot of hydrogen. Now follow that up with a little bit more of the reaction with water to make just completely CO2, not just carbon monoxide, and hydrogen. So you get 4 moles of hydrogen from, in the end, 1 mole of your methane. So that's how we make it. So what are some applications for this hydrogen that you just made? What can you use it for? Well, there's 2 big ones in industry you need to realize they use it for. One is they use it to change nitrogen. Now this is huge. Nitrogen is dang stable. It's got like a triple bond between the nitrogens. It's really hard to bust this up and make something with the nitrogen. I mean, we've got a lot of, it's like 80%, 78% of our atmosphere is nitrogen, but it doesn't tend to change into some other form readily because it's a triple bond between the 2 ends. Well, Haber, a German chemist, determined with metal catalyst we can take the nitrogen, bring it in with hydrogen in that atmosphere, and that high pressure, high temperature with a metal catalyst, you get a little bit of this ammonia formed. It's actually not favored, but if you keep pulling it out, according to Le Chatelier's principle, it'll keep making that NH3. You say, well, it's exothermic. Yes, but it's not favored. I guess Gibbs energy is not favorable. So we only get a little bit of it. The enthalpy is good, but the entropy sucks. I guess they're going from 4 to 2. So we're losing. But we can drive it still with a catalyst. We can use that to kind of keep the energy of activations down. We can make this and then siphon it off, and it'll continue by Le Chatelier's principles to make some more. We'll learn more about the Haber process. Just remember this is a very key reaction because we use these for fertilizers. It's for agricultural purposes. We need a lot of ammonia. We can make it now from a very stable into molecule by a Haber process. This is hard to break because it's very stable. But we figured it out, or I guess the chemist in the early 1900s figured it out. So the last thing we can do with hydrogen that I want to point out, there's many things, of course, you could do, but one of them is for fuel. We can take fossil fuels and we can remove our thiols. And you say, well, what's the big deal with having thiols? Well, they break down in oxidation to sulfur trioxides. That turns into acid rain, turns into greenhouse gases. So it's a very bad thing to leave this in your coal. Well, they can use another metal catalyst to bind, I guess, not just the S and the H's to this. You get some of the S with bond to this metal surface. The hydrogens come off and bond to the metal surface. We have the ability to bring these hydrogens and the S together off the metal to make hydrogen sulfide and siphon that off. And this is what we want to burn. This is our fuel. It now no longer has, when it is added to the other alkanes, it no longer has a sulfur in it. We can just have now more excess fuel added to that gas or to that liquid because we've taken all the S away. We have now a hydrocarbon that can be, along with the other fossil fuel, burned. Because fossil fuels plus sulfides is what we have often is a problem. We have impurities. Fossil fuels, hydrocarbons, but we have sulfides that we need to get out. So that's another application for hydrogen gas. I'm going to go a little bit more quickly on these last 2. So it turns out you can make sodium metal and lithium metal by electrolysis, but you have to have, I guess, with this technology, you better have no water present and no oxygen. We'll talk about why for both of those. If you have the ability to I guess, make lithium at this post, you better have no water present because you'll have, instead of lithium precipitating out, you'll have hydrogen gas generated on one side and chlorine gas generated on the other. So just in general, know that they have to take from brines in the earth that they suck out that has a lot of sodium chloride and a little bit of lithium chloride in it. They have to dry it out completely or use salt flats. No water, so this is pure salt, sodium chloride or lithium chloride. You heat it up, but of course if we start to precipitate lithium, at this post and you bring it out into an oxygen environment, it'll immediately start to burn. It's very reactive with oxygen. So we have to make sure no oxygen and no water are present when you do electrolysis of lithium chloride or sodium chloride salts. So there's a video, if you click on this picture, that talks more about that. So please check out all the hyperlinked videos in the notes that are in PDF form for you. There's one here also, it's a link. We can use that lithium that we made, that pure metal, through a few reactions. You can have the metal make what's called an organolithium. And we said that could be like a methyl group bonded to lithium metal. And I just want you to remember, when you see this, that means that I almost have a full negative on this carbon because the electrons still cheat because it's not very electronegative. They still cheat to the carbon. And if that's the case, this carbon can be used as what's called a nucleophile. You just need to know that that means it loves on a nucleus. So he can go and take his electrons and react with this carbon that has a partial positive charge, the nucleus of the carbon, and the electrons will get pushed up to this oxygen, and with a protic solvent we can cap it off, and we get, this is key, a carbon-carbon bond. There aren't a lot of reactions that give us in organic chemistry carbon-carbon bonds, but organolithium is one of them that we can use. You can't do that with sodium. So sodium cannot be used. That's a huge difference between these two. Sodium can make salts with oxygens, with nitrogens, negative on an N, negative on an O, but you cannot make, or not easily, the sodium bond with carbon and get the same sort of reactions you have with methyl lithium. You can't do that. And if you actually can make this, it's not soluble in anything except for polar solvents, like maybe THF or something like that. But what's so cool about the lithium salts is that these salts are soluble in hexane. It's crazy that you get a very reactive sort of polar compound with a very reactive carbon here, is the ability to attack a nucleus, but it's soluble in hexane. If you remember, hexane has no oxygens or nitrogens. It's a non-polar solvent. And one last thing, the form that these come in is often not what they call monomeric, meaning in solution when you dissolve it, it's just these two kind of floating around with each other. No, it turns out that you get these kind of groupings of the alkyl lithiums into either tetramers or hexamers, but they still, that's a grouping in hexane or some sort of nonpolar solvent. It still has very good function in reactions with other organic compounds. Now we're almost done. This is the last one, and I'm going to work from right to left here. Why? Is because these two are very similar. The Grignard reagents, where we use a magnesium, which is an alkaline earth metal with a +2 charge. Remember how we said the charge density is very similar to the +1 charge of lithium? And off of one side we'll have like an ionic bond, bromine, but on the other side there's a little bit of a covalent bond between the R group and the magnesium. But in the same way that we could use this to attack carbons, to make those very treasured carbon-carbon bonds, we can also use what's called the Grignard reagent. This R group also has the negative charge. So we can kind of say you can do the same thing that the organolithiums can do. They can attack a partially, now you tell me, what would the partial charge of this carbon be? If you have an oxygen off of it that's very electronegative, hope you're saying, oh yeah, that'd be partially positive. And I can bond that R group to a carbon through a carbon-carbon bond, and when we work it up with a proton, that's where this comes from. I want to stop there with this one and say, if we take these what we call sort of strong nucleophiles in terms of their reactivity, they're very aggressive, we can tone it down if we change the metal that's bonded to the R group to something like copper. If you look at copper where it's at in the periodic table, we're going to get to more of these transition metals in the next presentation. They're further, let me just draw underneath here, they're further to the right. So we have our lithium over here, and we have our magnesium. We're going to have copper down here. And as you go to the right, tends to be, not always, but as you go to the right, the metals tend to be more stable in the positive charge. They're not as, I would say, they're more able, let's just leave it at this, they're more able to make covalent bonds with the non-metals that sit over here. These are going to be very, very unstable bonds because you have something very, very electropositive and something very, very electronegative. This is not as aggressive towards the carbonyls. So what it tends to do, it still reacts as a partial negative, and this would be this would be a -1 charge. You got your lithium here, we have +1 charge. And this is, yeah, if I got that right. So this will take the partial charge. These electrons still cheat a little bit towards the R group, but not as much. Remember how we said this kind of has a little bit more of a sharing of that bond. We can have that R group not attack the direct position. We call this the conjugate position. It can be more selective in where it attaches. So you can do the same thing, though. In the end, you get a carbon-carbon bond formation, but just at a different location. That's maybe a good lead into talking about transition metals. Transition metals are not as sensitive to water. This would be very, very sensitive to water. This is not as sensitive to water in reaction with it, because the copper is a little bit closer to the right side of the periodic table, and you tend to find those kinds of transition metals like silver and gold on this side, which is kind of the more stable side of the transition metals. They don't have as much reactivity or sensitive to water and such. All right, thanks. Bye-bye.